So what area tends to pick up electrons? The right side. Yep, except for the last group. Noble gases don't. So they tend to pick up electrons, okay? So then the metals, everything else, kind of to the left of what we call the staircase sometimes, where we have aluminum, germanium, and those metalloids. Anything to the left of that, they tend to lose electrons to become positive values. So we have these things called cations and anions. First thing I'll talk to you about is that what happens to the size of the atom, and we'll do the easiest one first because it is definitely easy, when we have, for example, sodium lose an electron. So what happens to the size of the atom when sodium loses an electron? You can see that one real easy, can't you?
Yeah.
So here's sodium, and then here's sodium ion. Gets smaller, right? So everything that loses electrons 1, 2, or 3 is going to get smaller. Okay? Anytime something loses electrons, it's going to shrink down. Okay? So if we have magnesium, magnesium's in that same row. So we have magnesium start out. I'm going to make it a little bit. And we'll just do a different section. So then we got magnesium. And it starts out with 1 electron. Or 2 electrons out here. Okay? Then we lose 1 electron. What happened to its size? Got smaller. Okay, even though it has that outer level, it does shrink. Okay? Question is, why does it shrink? Well, what we're doing is we're getting rid of electron, but we have the same number of protons in the nucleus. And by doing that, it pulls in that outer level closer. Because what do we know about these 2 electrons here in that level? Do they attract one another or do they repel? They repel because they're like charges. So now we don't have electrons, 2 electrons in this outer level, they won't repel. So that's Mg plus 1. But Mg doesn't stay at plus 1. Mg will go to a plus 2. So then here's Mg of plus 2.
Which is the same as Na plus 1?
Which is the same as Na plus 1. Yep. And so everything, for the most part, I'm generalizing this. Everything's not always. But as sodium goes, it gets 8, it stops losing electrons. Magnesium, it has to lose 2, it stops, and we'll explain why here in a second. It stops, why it does not lose any more electrons. But I think most of you can realize the reason it doesn't lose many more electrons is because it's full. Any questions you have with that? Okay, so that, in a nutshell, we could do any of them and kind of show the progression of it losing electrons in which to get 8. Aluminum will do the same thing. If we did aluminum, it would lose 3. And then it would stop. Okay, so now let's look at an easy element. Let's look at fluorine. So fluorine has 2 and 7. then it gains an electron. And what happens to the size of fluorine?
It gets bigger.
It gets bigger. The reason it gets bigger is because now you got more electrons wanting to repel each other, and so they push out. So this is fluorine going to fluorine minus 1. So anions get bigger as they add more and more electrons, because as you're adding more electrons, there's more repulsion taking place between those electrons in that level. All right, so we do oxygen. Oxygen goes through also something real similar to it. So oxygen starts out with 6. Then it picks up 1. But it's not satisfied with 7. It wants to pick up another one. Oh, I messed that one up, didn't I? And then it stops gaining electrons. So it stops gaining electrons now. Because it has 8 also. So once it gets to what's called the octet of electrons, and it stops gaining electrons. Okay? Any questions you have with that? So if you have to compare sizes of atoms, I know there's one section that says, let's compare the sizing of these atoms, and you got something neutral, you got something minus, and you got something plus.
That was the one I asked you about yesterday.
Right. So the one that's minus is going to be the biggest one. The one that's plus is going to be the smallest one because it lost electrons, okay? Just because of the reasoning we went through. Okay. Last thing that I'm going to talk to you about has to do with ionization energy. So we're going to look at sodium here. Okay. So we have these, they're called ionization energy, and it's called ionization energy 1, and then IE 2. Okay, so to take out this first electron, it's going to be a lower amount of energy than to take out the second electron. You guys probably know why. Okay. So to take this electron out, it requires so much energy. But to take this electron out, or any of these electrons out, then IE2 is always going to be greater than IE1.
Is that because it's further away from the nucleus?
Yeah. Yeah. And also, it's got a full level. It's stable. You don't want to take an electron away from a stable element because then it becomes unstable. And it does everything it can to try to get that electron back. So it's not going to give up an electron because it's stable. When it has 8 electrons in its outer level, it's stable. Okay? Now, the last thing I'll talk to you about is this one, because this would be a good example. So, to take out one of these electrons, this would be IE1, and this would be IE2, and this is IE3. Of course, I'm going to use a greater than sign, and less than sign, but I'm going to show it by size. So I'm going to say this little one is that IE2 is a little bit bigger than IE1. Okay? But when I get to the IE2 to IE3, There's a big change.
So it's harder to take the one away than it is to take one when there's two on the outside?
It's easier. So IE1 compared to IE2, they're fairly close in their energies that it might be like doubling. Like IE1, IE2 might be you double the amount of energy you need to take it out. But if you go to IE2 to IE3, it's about 10 times it goes up. So between IE1, and I'm generalizing that because all of them have different numbers, but when we've looked at them in the past, there's huge jumps. Okay, in your book it shows an example for, I think, aluminum. In the first jump, okay, it's a little bit bigger, but then if you try to take out one of these electrons out of an atom, one, the electrons are closer to the nucleus, and two, it's stable. So you got two things working against it to pull out an electron. So you get huge jumps between the octet and the one with just one electron. You get huge jumps. Okay? You don't have to get your book out or anything. You guys have your book out. If you do, last thing I'm going to show you would be these huge jumps. Did anybody do something with ionization energy? There wasn't too many groups that did. The reason why there was huge jumps or big jumps in trying to pull out of an electron when we talked about ionization energy. But if you did, it's because the electron's getting closer to the nucleus. It's pulling it in, so there's greater force there. And so on page 285, it gives a great example of those huge jumps. Big jumps. So here's sodium. The jump goes from 495 kilojoules per mole of electrons to 4,560. That's almost 10 times. So trying to pull that out, it's impossible. Basically, it's saying it's impossible. It's like, okay, I can lift 100. Now put 1,000 pounds on the barbell. Let me lift it. Not going to happen. Not going to happen. Okay? This one. You look at magnesium. It starts out at 735. Then it about doubles the amount of energy you need to take out because the electron gets a little bit closer. And then you go to 7,730. So you got a huge jump. From the first one to the last one, it's about 10 times. About 5 times between the second and the third. It's just not going to do it. It's not going to pull it out. It's just too much work. Too much work. It's not going to... Now you can do it, you can pull it out, but it's going to be really unstable and it's going to find a way to get an electron from some other things. So, what do you got now? On page 284 it shows aluminum, the big jumps on that. That's kind of interesting too. So, 580 to 1815 and 2740, it looks like it's, goes up about 3 times and then goes up a little bit more and then it goes to 11,000. So it's just these big jumps. So that's why they stop taking out electrons or giving up electrons. Okay, that's it. That's all I have for, oh, no I don't. Sorry, one more thing. It's called PES. PES. It's called a photo, so if you've got a machine that counts electrons in the different levels, that machine is called a photoelectron spectroscopy, called a PES. And what it does, it shows peaks. So we'll look at the one on page 288. So you get a graph here. We never really did much with this in the past, but the last couple of years they have this on the AP test. So this is relative number of electrons. These peaks will represent a relative number of electrons. And over here it starts at 100 and it goes down. So it's like, it's kind of opposite of what you're usually thinking. You usually think about on the x-axis and y-axis is your lowest number and you go higher. Here you start out high and you go low. Alright? So this is fluorine. So you get a peak here, get another one here, goes along. Oh, that's boron. I don't want to do that one. Erase that. Okay, we're just doing fluorine. So there, goes along, get a peak there, here, that's it. Okay? So, what do you guys think this peak here represents? So here's fluorine. And pulling out electrons. So it takes 100 megajoules per mole of energy to kick out an electron. Where do you think those electrons are coming from?
The first energy level.
Yep.
First,
Two of them coming out. Okay? So, where's the next two come out? And I that's really not, I gotta get rid of one of these electrons. Okay, so where's the next one come out? So this would be the 1s2. What's that one? 2s2. Guys, see its relative number lines up there. They line up the same height. So we're taking out 2 electrons there. We're taking out 2 electrons there. And so what do you guys, what's this one?
3.
Not 3, but
2p5.
2p5. It's, there's 2 electrons. You go up a little higher, 2 electrons, and then you go a little higher. That represents 1 electron. So relative height to this one, it looks like it's little over 2 times as high. So that would be fluorine. And so what you can do with the graph, you can identify an element by looking at its relationship. And then, so then when you look at boron, I'm going to do that in a different color. So then boron goes along, I might as well do it in blue like they have. Goes along and it looks like you got one here, and then you got one here, and then we got one here. So what do you guys think this one is here?
1s2.
That's the 1s2 for boron. And this is 2s2. And then this is
2p1.
2p1. I mean, it's kind of cool that you can see that. You can see. Now, does it, it's saying it's taking, it's taking less energy to take out the first electron of boron versus fluorine. Does that make sense?
To take it out, yeah.
Because
It's gonna be
boron's a
really
bigger
hard
atom.
to take,
So boron's bigger. So that electron's farther away. So that makes sense. And if you look at the relative size, this is going to be half the height of that one. So those are PES. And it just goes along with trying to pull out electrons and ionization energy, and that's kind of how it works. So you'll have a couple questions on that. I think maybe if you came across them, you'll have some questions on that. So I'll let you go ahead and finish that assignment up.